Hello, everyone. Welcome back to week 1, Introduction to NDT. In the second lecture, in this lecture, we'll cover two learning objectives. First, we'll understand what is the commonly used non-destructive testing, and then we will talk about what are the typical NDT methods versus destructive testing methods. So let's begin. First, let's take a look at what is the definition of the NDT methods. Recall from last class, we talked about NDT is wide range of the testing and analytical methods used by various industries, primarily civil engineering, structural engineering, nuclear engineering, aerospace engineering, material science, and metallurgy industry. Those industry to use those testing methods to evaluate and characterize the property of the material components and structural systems without causing any damage to the tested part. Primarily, people are looking for discontinuity or the defects. NDT often refers to NDE, non-destructive evaluation, or NDI, non-destructive inspection. Typical NDT methods can be grouped into two categories. One is wave-based NDT methods. In this group, people often use acoustic wave to generate either vibration or the sound in the testing objects, and based on the signal received to detect the material property. Specifically, we have ultrasonic inspection, acoustic emission, ultrasound methods, electromechanical impedance methods, and another type is electrical or magnetic based methods, which are typically including eddy current, thermographic, radiographic, and the distributed sensors. And other type is visual inspection, fiber optics, and the arid sensors. For visual inspection, it's actually often underlooked. However, this is a very, very powerful tool, and particular for surface-induced defects. Probably the most common and the least expensive NDT methods is visual inspection. Of course, it relies on the inspector's eyes, visual ability to identify the defects and flaws, and which is very commonly used, particularly in bridge deck and civil engineering. And actually, 85% of the surface crack is identified by visual inspection methods. One of the major defects of these methods is internal defects cannot be identified. Sometimes needs to be aided by liquid penetrant. Use the color, dye, or fluorescent to highlight the defects, and particularly if the defects getting to really small in the mechanical machine part. We will dive into more in depth of these methods in the next few courses. In this slide, I would like to show you a couple examples how the instructor used the high contrast liquid, it's also called the dye, to enhance visual effect for very small crack, particularly the fatigue-induced small cracks on the machine part. So this is really highly depends on the skills and the experience which can be done in this continuous line, so it can be very productive. Again, the details of these methods and the limitation advantages will be discussed in the future course. So in this slide, I would like to talk about what are the typical defects we would like to see in a bridge deck. In general, there is a defects that would happen on the surface. For instance, you have a surface thermal induced crack or fatigue induced crack, And or you could have a delamination between the concrete and the reinforcement, um, or we could have a delamination. The delamination could happen on the top layer, could happen even in the bottom layer. And other than that, for instance, the steel could be exposed to the corrosion, and the concrete are also prone to the corrosion, and particular if the bridge is over the seawater, and some of the degradation of the steels and concrete would happen that can often happens to the bonding part. Other than visual inspection, acoustic emission is one of the often used methods for bridge inspection. So here is example. On the left, the inspector is use a chain, right? So we call it, this is chain drag methods. Drag a metal chain on top of the bridge deck, and by listening to the sound rebounded back to the inspectors, they can identify whether there is a delamination on the bridge deck. So this is typically um, induce a very quick transient stress by release the energy, and then based on materials acoustic property, we can identify if there is the defect or not. Again, the detailed explanation and underlying physical principles will be discussed in course number 2. Here is the application of how we use acoustic emission methods to detect the crack in the slab for the asphalt pavement. So here is the damage detection for uncracked slab. As you can see by looking at this frequency versus the power output versus frequency curve for uncracked slab. Other than your very prominent resonant frequency, and on the higher frequency side there is no AE signature. However, for the lightly and then heavily cracked slab, we can see a very clear acoustic emission signature. And so therefore, based on this results, we can identify whether there's a another type of similar wave-based methods, which is often used, is called ultrasonic testing methods. The principle of the ultrasound is to induce a high-frequency sound wave in the material, and based on the wave received, we can testing if there is if the crack or not. Again, because of the different materials density, materials modulus will affect the wave transmit in the material. That's what we call wave stress relations. We will explain that in week 4, wave stress relation. So for instance, in this case, this is your original wave, and this is the reflected back echo. This is a defect echo, or what we call DE. So by looking at the amplitude, which is the energy reflected back with the time domain, and then we can understand whether there is a defect in the material or not. Here is the examples to show you how we use ultrasonic testing for pipeline inspection, and then basically we generated a high frequency sound from the kilohertz to gigahertz into the material. In this case, it's a pipeline, and then based on how the reflectance and the scattering attenuation of this wave, and then we can identify if there is a defect or not by in this particular case we use what we call the A scan. So in the course 2 we will spend 1 week to discuss the underlying property of this material. We will talk about physics, and then we will talk about how we process the signal, and then looking at all the different scan, and then the specific property can be obtained from this image. Another similar type of the methods, which is called the electromechanical impedance methods. So in this case, we use a piezoelectric sensor attached on the concrete by giving an AC signal to vibrate the sensor. So the sensor will send elastic acoustic wave, and then based on the wave transmission and the reflection and attenuation, we can understand the stiffness of the material. So the reason is called the electromechanical impedance, because we specifically looking at impedance, mechanical impedance, which is the force over velocity of this particular wave. Of course, is over the time, right? Derivative of them. And so therefore we can understand the material's stiffness, material's defect. In this slide, I would like to show you how we use a very thin layer of the PZT to understand the strength of the concrete development over the time. As you can see here, we bound a PZT sensor on concrete and then to vibrating the sensor. So the sensor will send the stress wave into the concrete. And when water aggregates and cementitious material go through what we call the hydration process, they will generate CSH gel, right? Calcium silicon hydride, and which is the strength contributor for the concrete. And once cement is going through the hydrating process, the stiffness is increased. So therefore, the impedance of the material will be increased. So by looking at this specific impedance property, we understand the stiffness development of the concrete. So in this slide, I would like to change a gear a little bit to show you electric-based methods or electromagnetic-based methods. More specifically, in this particular case, we use the X-ray or gamma ray, and to looking at the internal defects of the objects. And this is very commonly used in the medical image, or the oil and gas pipeline image has been shown here, and people can looking at all the defects and the welding part of the pipeline. Other than radiographic eddy current inspection is very common in nuclear engineering, in oil and gas, and also in civil engineering to detect the cracks and to looking at the thickness changes and the residual stress. The basic physics is built on electromagnetic induction. And then we understand the Faraday law, right? Your EMF equal to minus N phi B over T, right? So Faraday law is basically say if I have a change of the magnetic flux in time, that will generate the EMF, and then the amount of the EMF equal to minus N, which is numbers of the coil, numbers of turns in the coil, and over the magnetic field divided by the time, derivative of the time. So the basic principle of this method is to use the AC current to induce a magnetic field in this probe, which is your primary magnetic field. And then when this primary magnetic field getting close to the metal sheets as being shown here, this is your testing object. So this magnetic field will induce what we call the eddy current. And then this eddy current will be detected by the probe itself because the secondary magnetic field will have opposition to the primary eddy current, to the primary magnetic field. And that change will be sensed by the probe and detected by a scope attached somewhere here. And then basically by looking at the eddy current, and then we can understand if there is a defect, because if there is a defect, the eddy current will be changed, and particularly the impedance of this eddy current will be changed. And we will talk about more details in the course number 3, and we will explain what exactly this eddy current testing, what is the impedance included, and how we use the impedance signature and to detect if there is a crack, if there is a thickness change, if there is a residual stress, or if there is a corrosion in the metal part. Again, the methods of this is very straightforward. It's built on electromagnetic induction. However, the entire setup it's quite complicated, and then we can discuss that in details. So here is to show you how people use the eddy current to understand if there is any fatigue crack induced in this pipe, or if there is a corrosion, right? So by looking at the eddy current pattern, if there is a crack, then the eddy current will be changed, the impedance will be changed, right? So your real part, which is your R, and your imaginary part, which is your RL, right? Or some people say it's XL. Your reactive inductance and will be changed. Your impedance probe, right, will be changed. So by looking at this change, we can understand if there is a crack. Another type of commonly used methods is magnetic method. Magnetic methods is to apply magnetic field internally or externally in the material and then use that to identify the defects. Basically, we use the small ferromagnetic particles and go through the material, and then if there is the defects, depends on the orientation of the defects, and that will cause the magnetic flux leakage, and then that's going to push the particles out. For instance, in this case, we can see this purple color and showing in the surface, so that's highly likely there may be some small fatigue-induced defects in these parts. So again, the detailed information about those testing methods will be introduced later in the course. I hope you have a brief understanding of what are the primary or the commonly used NDT methods will be discussed in this class. And with that, we would like to wrap up this short video, and coming next is a typical failure mechanism, and particularly what are the typical defects and the discontinuity can be induced in the material or structures.